All right, let's get started with section 3.5. Before we derive, I want to make sure that you're caffeinated. You never want to derive while you're sleepy. Let's get started, section 5. We're going to take derivatives of trig functions now. We have already talked about, tangentially, see what I did there? We've already talked briefly about what would the derivative of sine look like? What would the derivative of cosine look like? This has come up in warm-ups. This has come up, I think, in an activity sometime earlier on in the trimester. But it turns out that the derivative of sine of x is actually cosine of x. And so you might think about why that is. Just briefly, why would the derivative of sine be cosine? Well, one way to think about it is if sine is defined as the height of a point in the unit circle. So you don't need to write this down, but here's our unit circle. We take any point here, right? If we define sine as the height of the point, sine of theta, okay, so where theta is this angle right here, if that's the height, and cosine is the horizontal distance, or the run of the point, you might say. So this is cosine of theta. And the question is, well, when we ask for the derivative of sine, that's asking how fast is sine changing as theta changes. Now, what is the rate of change, or a function that gives the rate of change? Well, you can see that as the point moves around, that cosine is going to be changing in relation to sine. Both of those things are going to change at, what would you say, related rates at some level, okay? So that's the connection there. We're not going to go too far into it, but you can imagine that, when you're deriving sine, you're not going to end up with the derivative being, x to the fourth power or something like that. All right, you can also see that from the graph as well. The derivative of cosine, though, is not just sine, so be careful with this. It is negative sine. We're going to start with those two. I got to turn my autofocus thing here, make it stop. We're going to start with those two, and then we'll come back to the other ones. All right, so we'll start with sine and cosine. We'll do some problems with those, and then we'll come back to tangent, cosecant, secant, and cotangent. So first example here. All of the rules that we learned previously still apply. For instance, if I want to take the derivative of f of x equals sine of x minus 2 cosine of x. Okay, so to take the derivative of that, what we would do is just derive each piece individually. So f prime of x here would equal cosine of x minus, and then if we're going to derive 2 cosine x, that's the same as 2 times the derivative of cosine. Well, derivative of cosine is negative sine, so I will have minus 2 times negative sine. That's going to end up being plus 2 sine of x. Okay. So there's the derivative on that one. All right, next. Let's do another one. Let's integrate another rule here. So we had the sum difference rule here for derivatives, but let's try a different one. So let's go y equals x squared sine of x. And by the way, the instructions here are to take the derivative. All right, so what I have here is x squared times sine of x. I have a product, okay? So I'm going to have to use the product property of derivatives. To do that, I'm going to get dy dx, the derivative of y with respect to x. Remember, the product rule goes something like the first times the derivative of the second plus the second derivative of the first. So this would be first, so x squared, times the derivative of the second, it's cosine x, plus the second times the derivative of the first, which should be 2x. All right, there's not a lot to clean up there. Probably if I was writing this as my final answer, I'd go x squared cosine of x plus, and I'd probably put this 2x in front, 2x sine of x. Just so you don't get confused, as whether the 2x is inside of the sine or not, okay? So there's the final answer on that one. We can also use a quotient rule. Might as well do one with the quotient rule here. So let's go y equals cosine of x divided by 1 minus sine of x. As I've said many times, you should give this one a try on your own. Pause the video and then play it through and see how you do. Let's give myself some more space here. Get rid of that. Okay, now, okay. Excuse me. So, quotient rule. bottom times derivative of the top. So 1 minus sine times the derivative of the top. So that's negative sine. The derivative of cosine is negative sine. Minus the top, which is cosine of x, times the derivative of the bottom. The derivative of 1 minus sine. Well, derivative of 1 is 0. Derivative of negative sine. Well, the derivative of sine is just cosine, so it'll just be negative cosine. This is all divided by the bottom squared. So 1 minus sine of x squared. Clean up. So what I end up with here is negative, as I distribute this negative sign out here and here, I get negative sine of x plus sine squared plus cosine squared. All divided by 1 minus sine of x squared. Now, when you see sine squared plus cosine squared, some sort of bell should go off in your head that this right here is 1. It's a trig identity that you might remember from pre-calc. It's sine squared plus cosine squared is equal to 1. So our final answer then here for the derivative will be 1 minus sine of x divided by 1 minus sine, whoops, hold on. Yeah, 1 minus sine of x squared. Oh, hey, look. I got 1 minus sine of x on top, and I have 1 minus sine x squared on the bottom. So this will simplify to 1 over 1 with the 1 minus sine of x in the bottom. So I'll just get 1 over 1 minus sine of x. All right. So there's my derivative. That was fun. Let's try one. Let's talk about taking antiderivatives of trig functions. The thing about taking antiderivatives of sine and cosine is that you are essentially you just have to think in reverse. There's no good, clean rule like there is with the power rule, the anti-power rule, I guess you would say. So if we have this example, 3x squared plus sine of x plus cosine of x dx, right? So remember that all of this notation for you just means take the antiderivative of this thing that is in the middle, okay? So in other words, we want the function whose derivative is 3x squared plus sine x plus cosine, okay? The way that we're going to approach this is we are going to, in fact, we'll even write that. We want a function, and whose derivative is that? The way we're going to approach this is just piece by piece. We're going to use the sum property. Works for antiderivatives as well. So what is the antiderivative of 3x squared? Well, the rule is add 1 to the power and divide by it. So I'm going to get 3 divided by 3. That's 3 over 3, which is 1. So I think this will just be x cubed. All right, so I have x cubed. And then what's the antiderivative of sine? Well, the derivative of sine is cosine. The derivative of cosine is negative sine. So I think what we want here is negative cosine of x. Now, what I tell students all the time is if you think that you've got it wrong, I like how that gray looks. If you think that you've got it wrong, take the derivative and see what you get, right? You should always check your answer, and it's quite easy to do here. So if you take the derivative of cosine, you'll get negative sine. You'll have negative sine, which is positive sine. Okay? Anti-derived cosine, you get sine. Don't forget the plus c. Okay? All right. Okay, let's talk about the other ones, the other derivatives. So it's tangent, secant, cotangent, and cosecant. And here's what I'd like you to observe. Every one of those trig functions can be written in terms of sine cosine. So tangent of x can be written as sine of x over cosine of x. All right? And because of that, if you forget any of the rules other than sine and cosine, derivative rules, then you can work back to the other derivative rules by changing them to sines and cosines, okay? So to do that, we will just, if this is our function, y equals tangent of x, then what we'll do to take the derivative of this is we'll use the quotient rule. So dy dx, again, if our function is tangent, is going to be equal to, apply the quotient rule here. So this is going to be bottom times the derivative of the top. So I guess let's use parentheses here, cosine of x, minus the top times the derivative of the bottom. The derivative of the bottom is negative sine all divided by the bottom squared. I just write cosine squared x. Remember that cosine squared written like that just means the same thing as cosine, the entire thing squared. All right, so let's clean up. So I will get cosine squared plus sine squared x, all divided by cosine squared x. Oh, cosine squared plus sine squared, that's 1. Okay, so this is going to be 1 divided by cosine squared x. And 1 divided by cosine, I remember that's an identity. 1 divided by cosine is secant. So this can be written then as just secant squared x. There's your derivative of tangent. I'm not going to go through and prove all of these in the book. There's a couple that you have to go through and prove. But yeah, so any of these can be derived from not quite first principles, but from just knowing the derivative of sine and cosine. So let's go back and fill in our chart here then. I'm not going to do that for all of them, like I mentioned. Let's go back and fill in our chart. The derivative of tangent of x is equal to secant squared x. The derivative of cosecant turns out to be negative cosecant cotangent. So negative cosecant x cotangent of x. All right. Derivative of secant is secant tangent. So secant of x tangent times tangent of x. Okay. The derivative of cotangent turns out to be negative cosecant squared of x. Right? So there is all 6 of your rules. There's a little bit more in this lesson that I'd like to go through, but I think that's probably a good spot to stop for this part of the lesson. We'll talk a little bit more about higher order derivatives, and in the next video we'll also talk about jerk. It's one of my favorite concepts.